Picture this. A satellite is hurtling through the vacuum of space at thousands of miles per hour. And yet, it manages to keep its antenna pointed perfectly, and I mean perfectly, at Earth. Have you ever wondered how it actually does that? It's a genuinely high-stakes problem. I mean, if that antenna drifts even a fraction of a degree, we lose communication, our GPS navigation goes down, and billion-dollar aerospace missions are just completely compromised. The secret to keeping it locked precisely on target isn't magic, and it isn't just heavy machinery. It's actually a very specific, highly reliable kind of math. Welcome to today's Explainer, where we're going to dive right into it.
Our source material hooks us immediately by describing this mathematical solution in such a cool way. It calls it a mathematical machine that turns vectors in space without changing their size. I absolutely love this framing. We are definitely not going to look at intimidating, abstract, unreadable equations today. Actually, scratch that. We're going to look at perfectly predictable mathematical machines. These are machines with specific gears, strict rules, and incredibly practical real-world applications that literally keep our modern world spinning.
So what exactly is this machine? Well, it's called a rotation matrix. By definition, it's a matrix used to rotate vectors or coordinate systems in space while preserving key structural properties. Whether you're dealing with foundational linear algebra, programming a robotic arm in a car factory, developing spacecraft attitude control systems, or even just rendering 3D graphics for your favorite video game, this matrix is the fundamental tool. It's the exact thing that tells an object how to spin smoothly without breaking apart or losing its shape.
Here is our roadmap for today. 1. The mathematical machine. 2. Spinning in 2 dimensions. 3. The rules of rotation. 4. Entering the 3rd dimension. 5. Spacecraft and advanced navigation. And finally 6. The catch.
Okay, let's jump straight into Section 1, the mathematical machine. We need to look at what it does, and, just as importantly, what it doesn't do. So let's look at the strict boundaries of our machine. On the left side here, we see exactly what our machine preserves: length, angles, the overall shape, distances, and orthogonality, which, by the way, is really just a fancy math term for keeping things perfectly perpendicular. Basically, this is a very safe shape-preserving machine. It guarantees your object won't get distorted during a rotation. Now, on the right, notice what it absolutely does not do. It will never stretch, skew, or change the magnitude or size of your vector. It strictly turns it. Nothing more, nothing less.
Moving on to Section 2, spinning in 2 dimensions. Let's build the foundation before things get too complex.
Imagine a standard flat 2-dimensional graph. To achieve a counterclockwise rotation by a specific angle, we'll just call it theta, we use a basic 2D matrix made up of cosine theta and sine theta. I want you to think of these trigonometric functions, the sines and cosines, as the actual physical turning cogs of our machine. When you feed a vector's coordinates into this matrix, those sine and cosine gears turn, they calculate the new position, and boom, they output the exact coordinates of your new rotated vector.
Let's actually test drive this and walk step by step through a 90-degree rotation. Just to show you that this math really isn't magic, it's a highly logical procedure. Step 1. We start with a vector resting completely flat on the x-axis at coordinate 1, 0. Step 2. We apply our 90-degree matrix. Now, because the cosine of 90 degrees is 0 and the sine is 1, our matrix simplifies perfectly to a little grid of 0, -1, 1, 0. Step 3. The machine runs its calculation and we arrive precisely at our destination vector, 0, 1. It's pointing straight up on the y-axis now, exactly a 90-degree turn.
Section 3, the rules of rotation. Let's look at the non-negotiable properties.
Okay, for a rotation matrix to actually be mathematically valid, it has to follow a strict rule book. First up is orthogonality. The rows and columns must be perpendicular unit vectors. Second, the determinant must equal exactly 1. And guys, this is a vital failsafe. A valid matrix has a determinant of 1, sure, but if it accidentally had a determinant of -1, it would mirror your object. It would literally flip it inside out. So having the determinant equal 1 is exactly what stops our machine from reflecting the object, ensuring it's performing a pure, pristine rotation.
Time to level up. Section 4. Entering the 3rd dimension. The x, y, and z axes.
Take a look at these 3 matrices side by side. It honestly illustrates the beautiful symmetry of the formulas. These are the standard matrices for rotating around the x, y, and z axes. Notice the patterns in the columns and rows? The number 1 and the zeros act as kind of an anchor, locking the axis of rotation safely in place, while the sines and cosines spin the other 2 dimensions around it. You really don't need to memorize these massive grids to see how the cogs turn.
You can visibly see the structure of a 3D spin right there in the layout.
Which brings us to Section 5, Spacecraft and Advanced Navigation. This is where those real-world high stakes come back in. Aerospace engineers rely on these rotation matrices for almost everything. I'm talking about transforming Earth-centered inertial coordinates to Earth-centered Earth-fixed coordinates, or translating between a spacecraft's internal body frame and the external inertial frame of deep space. They use them for determining spacecraft attitude, pointing those antennas we talked about, and mapping orbital mechanics. Seriously, the next time you open a map on your phone to find a coffee shop, remember that converting your satellite coordinates from inertial space to Earth-fixed coordinates requires these exact Earth rotation matrices running flawlessly in the background.
But there's always a twist, right? Section 6, the catch. Let's look at composition and limits.
So, here is the absolute most crucial thing to remember. Look at this mathematical reality. Rotation x times rotation y does not equal rotation y times rotation x. In math terms, matrix multiplication is absolutely not commutative, but in plain English, it means order matters immensely. If you rotate a spacecraft around its x-axis, then its y-axis, you'll end up in a totally different physical orientation than if you did y first, then x. If a programmer gets the order wrong in their code, you don't just get a math error, you might get a tumbling, completely out-of-control satellite.
Now, to manage these complex sequential rotations, we often generate our rotation matrices using Euler angles. You might recognize them by their common aviation terms, roll, pitch, and yaw. It's a super intuitive way for human beings to describe orientation in 3D space, just taking it one axis at a time.
But, and this is a big but, this human-friendly intuition comes with a mechanical flaw. Euler angles can suffer from a disastrous mathematical singularity called gimbal lock. This happens when two axes perfectly align and suddenly, boom, you lose an entire degree of freedom. Your machine gets stuck. To avoid this nightmare entirely, engineers often have to pivot to more advanced mathematical systems. So instead of basic Euler angles, modern spacecraft software often relies on quaternions or direction cosine matrices to ensure the ship never, ever loses its bearing, no matter what kind of crazy maneuvers it's pulling.
Which leaves us with a pretty fascinating final thought to wrap up today's explainer. We've mapped the stars and navigated the entire solar system using these foundational rotation matrices. They are literally the mathematical machines that built modern aerospace. But as we venture even deeper into space, and as our spacecraft become increasingly autonomous and complex, will advanced lock-free systems like quaternions completely replace the mathematical machines that got us there in the first place? It's a question that sits right at the cutting edge of modern innovation. Thanks for exploring this with me. Keep asking those big questions, and I'll catch you next time.